Hello, welcome to our semiconductor education program. This is Vincent Chang. Today we are going to continue our lesson on the subject of bistable multivibrator and focus on another one called non-inverting bistable multivibrator, also known as non-inverting Schmitt trigger. Non-inverting Schmitt trigger. So here's the circuit. So two important characteristics. The first one, positive feedback loop. The second characteristic, the input signal, the VI external input signal, is going into the non-inverting terminal of the op-amp instead of the inverting terminal, which is you learned from the previous lecture, inverting bistable multivibrator. This is the non-inverting configuration. All right. So that's one of the major tasks of this lecture. The key takeaway is the learning objective is you are able to harness this circuit to handle the transfer characteristic, which is nonlinear. All right. The nonlinear transfer characteristic of this bistable multivibrator, VO versus VI. Because the nature of the positive feedback tells us there are only two stable states. VO capital M, V capital M, the red state, or the blue state, V lowercase m. So it depends on the comparison of the V positive and the V negative, which is connected to ground. So it seems easy. If V positive is higher than 0, then red state, right? If V positive is lower than ground, is negative, is lower than 0, then blue state. So now, if it seems easy, then let me encourage you to take 5 minutes, try to figure it out. The two threshold voltage, which VI should compare with. The two threshold voltages, VT positive and the VT negative. The one threshold voltage for the red state and the second threshold voltage for the blue state. So let's pause for 5 minutes. I'll be back in 5 minutes. So I'm back. Can you figure this out? If you can figure this out in 5 minutes, and if you learn this circuit for the first time, you are very, very smart. I have to say, you're very smart. So it seems easy, but it's not, right? So first of all, you have to figure out, so who controls the V positive voltage, V positive? Depends on the VO and the VI. So you can apply the principle of superposition and put down this. So I will pause to take note on this, all right? So V positive depends on the part of the contribution from the VI. You can set VO equals 0. So which gives you R2 divided by R1 plus R2. And then the second contribution from the VO, you can set VI equals 0. So then VO times what? R1 divided by R1 plus R2. All right? So this is the V positive voltage. And then I said this about 6-7 minutes ago. I said if assuming you take 5 minutes to figure this out, okay? And then I said, it seems very easy. If V positive, if V positive is positive, then red state, VO was high. If V positive is negative, is less than 0, then blue state. So the threshold voltage, the critical point is when V positive equals 0, right? So you plug in the VO equals the first stable state. And the command V positive equals 0. And you plug in the VO equals V positive. Then the corresponding VI will tell you the threshold voltage for the rest state, which is a negative value. All right? Are you with me? A little bit headache? Let me repeat that. Let's go back. Now you try to figure out the threshold voltage, right? So what's the threshold voltage? The ball, when physical analogy, when the ball on the top of the hill, corresponding to the situation when V positive equals V negative, which is connected to 0, right? So we simply command V positive equals 0. And when you plug in VO with, replace VO with the rest state output, then the corresponding VI will tell you the first threshold voltage, which is the red threshold voltage, and it's a negative value. It's a negative value. So you solve this, solve VI, which tells you negative V capital M times R1 divided by R2 is a negative value. So the first threshold voltage now is solved. Let's move on to the second threshold voltage, which is corresponding to the blue state. You do this again. Command V positive equals 0. And plug in. Replace VO by a blue output voltage. Blue saturation voltage. So when you replace VO by the blue saturation voltage, the corresponding VI will tell you the second threshold voltage, which is the blue threshold voltage, and it's a positive value. It's positive. Okay? It's a positive value. I know it's a little bit confusing. A little bit confusing. So now you see the two threshold voltage. This is why I do this on purpose. Intentionally put the red correspond to red. The blue corresponds to the blue. You just don't mess up with this color, okay? There's a meaning. This is the bistable. So we need two colors to represent the two stable states. All right? So I'm thinking about the test. Okay, so this is very likely you will see this on maybe you do the final exam. Okay, so I don't mind, and I will appreciate if you prepare two color pen. Okay, to associate with, to highlight the two state, and it also actually helps you. It helps you to tell you, signal you that, hey, now we are on the first state, the rest state, or we are at the blue state. So now the VO, the rest state. There are two stable states. You can go through any positive feedback loop. So assuming that start with the rest state, then which threshold voltage you are supposed to compare with for the VI? The red threshold voltage, which is the negative. You know why I'm laughing? If you are very familiar with the circuit you learned from the previous lecture, which is exactly opposite of this one. The previous lecture I told you when the rest state and threshold voltage is positive. You can just pause and go back to the previous lecture and see. Check what I just said. But this one, when you're on the rest state, at the rest state, the threshold voltage is actually negative. Okay? So it's very natural that you confuse a little bit for the first time, second time, and you finally know the subtle difference between these two bistable multivibrator. Let me just try to finish this, okay? Let's try to finish this quickly. So now we are in the rest state. Rest state. VO equals high. Then what? The reason you can stay on at high state, the rest state, is because the V positive is greater than 0. It's because the VI is higher than the red threshold voltage. So as long as VI is higher than the red threshold voltage, which is VT negative, then this state can be remained. So let's try to lower the VI. Then V positive is lower. This is ground. So V positive is here. If you lower the VI, because the V positive is proportional to the change of the VI, the change of V positive is proportional to the change of VI. So if you lower the VI, going backward, okay? Watch the just pay attention to a transfer characteristic. I'm talking about the transfer characteristic. If you lower the VI, then V positive is going down. This is ground. So when you reach the ground, then which associate with the threshold voltage, associate with the bar on the top of the hill, then what? If you lower VI just a little bit, then switch happens. VO, the output going from high to low, from red to blue. So the moment when the output switch, remember the subtle, but it's very important and it's very subtle. This is the key. When the output change state, then the threshold voltage will change immediately and accordingly. Okay? So now we are located on the blue state. Then which one you are supposed to compare with? The blue one. Okay? So when you change state, you immediately, your previous focus on the red threshold voltage. But once you change state, you forget this. And you focus on the blue one. Okay? You focus on the blue threshold voltage. The reason why the circuit can remain at the second stable state, the blue stable state, is because the VI is less than the blue. The VI is less than VT positive. So when VI is less than VT positive, which means this is ground, which means the V positive is here. Okay? V positive is here. And then if we gradually increase the VI, gradually push the VI, increase the VI, then the V positive will increase accordingly, proportionally. Then until this happens, threshold voltage, the top of the hill, and then what? Then switch happen. Then the state will go back to the rest state. When you go back to the rest state, when you step on the rest state, when you stand on the rest state, then you focus on what? The red threshold voltage. And the reason why you go to the rest state is because of you cross the blue threshold voltage. So this created this kind of the hysteresis, which we talked about in the previous lecture. All right, so the arrow is important. I said this in the previous lecture. I said today's performance, today's behavior depends on the history, depends on where you come from. You come from the rest state, the VI going down, or you come from blue state, the VI going up. If VI located between the two threshold voltage, between the hysteresis window. So now, here's the summary. So this is the summary. Okay, on the left-hand side is the inverting configuration. On the right-hand side is the non-inverting configuration. So here's the takeaway. Two bistable multivibrator. The left-hand side is the inverting. Excuse me, maybe the slide, the capture is not very well. So the left-hand side is inverting. We are going to the negative input terminal. The right-hand side, your right-hand side is the non-inverting. So let me show you the result. Quickly review the result. On your left-hand side, for the inverting, the red threshold voltage is positive. But on the non-inverting, the red threshold voltage is negative. And I said the arrow is very important. And this one, for the inverter, just take out your watch, okay? So this one is what? Is what? It's clockwise. The hysteresis is clockwise. And this one, just look at your watch, okay? Is what? It's counterclockwise. All right? So inverting, non-inverting, the threshold voltage is opposite, and then clockwise hysteresis on your left for inverting, and counterclockwise on your right for non-inverting. This is the major takeaway of this lecture. In the next lecture video, I'm going to teach you how to apply this to creating another type of multivibrator, which is called a stable multivibrator. And I'm going to teach you how to design, how to analyze a square wave oscillator or square wave generator. So look forward to seeing you in the next lecture. Thanks for watching.